in order to generate the causal effect, you need to include all the variables that affect y, that affect y, and are correlated with x1. And as we discussed, that's less stringent than including all of the variables that affect y, because you can come up with variables that might affect y, but that won't be correlated with x1, for example, as group 7 did there. Despite that fact, the list of variables that you need can often be very long, and you might not be able to get data on all of those variables. So if you don't have data, like you don't actually observe a given variable, then of course you can't include it in your regression model. And in that case, then you're not going to be able to hold this emitted variable constant, which is why we call result bias emitted variables bias. Sometimes we'll also refer to it as selection bias. That's a little bit more common when we're talking about like data that are measured at the individual level, because then what we're thinking of is that we have data on individuals, and maybe they're like going into some sort of program, be it like a training program or a welfare program or something. We want to estimate the effects of going into that program, and we think people are self-selecting into that program as opposed to being randomly assigned into the program. So sometimes we'll call selection bias. So the same thing as emitted variables bias. So given that we have the potential emitted variable bias in a lot of observational data sets, we need to come up with ways to try to at least address it. And so one way that or really a very generic way that gets operationalized in many different ways, but the way that we often try to do that is to essentially find a control group that mimics the treatment group as closely as possible, and then do a comparison between those two groups. So let's suppose that we want to estimate the effect of a policy, which is often what our goal is with these types of analyses. And so we code the policy as a binary variable, which we'll call x. And to continue with kind of like our pollution example, we could imagine that there was an EPA, Environmental Protection Agency policy that reduced air pollution in Los Angeles. So x is going to be pollution in Los Angeles, or really pollution in a given area, and then y is going to be daily hospitalizations. And so we want to estimate the effect of that policy on hospitalizations. So we run a regression of y on x. But other factors that affect hospitalizations might change around the same time as the policy. So we'd be worried that there could be emitted variables bias. So, like sort of simplest way to say this is maybe we would observe a change in hospitalizations, like a reduction in hospitalizations after the EPA policy comes into effect. But we don't know whether or not that's just some sort of downward trend in hospitalizations that would have occurred anyway, even without the policy, and was caused by some other factors versus being an actual effect of policy. So the multiple regression solution would be to try to control for all of the potential factors that might affect hospitalizations and could have changed during this period. But as I just said, like, it could be difficult to get data on all of those factors. So instead, what you'll often see people do is what we call differences in differences, which is to find some sort of control group that we think is similar to Los Angeles and that we can gather data on, but is going to be unaffected by the policy. So the idea here is that the control group is going to tell us how the outcome, which in this case is hospitalizations, would have evolved in the treated group absent any policy intervention. So there's this really important assumption, which is going to sort of come up repeatedly in different contexts depending on the studies we're looking at. But the key underlying assumption here is that any factors that affect the outcome that change in the treated group also change by sort of a similar degree in the control group. So if that's true, then basically the change in the outcome in the control group is going to capture the net effect of all of the changes of these omitted variables. So in the air pollution example, let's suppose that there were an EPA policy that took effect in Los Angeles at the very beginning of 2010, and then let's suppose we wanted to use San Diego as the control group for Los Angeles, right? So the motivation here would be that San Diego is also a city in Southern California. It's likely to be sort of affected by many of the factors that you would think would potentially impact hospitalizations and air pollution in Los Angeles. So things like the weather systems in general, like annual weather patterns should be similar. Economic growth or recessions or so forth should also be similar because the two areas are so geographically proximate and would have somewhat like linked labor markets, at least to some degree. And furthermore, assuming that the same policy didn't take effect in San Diego during that period, then it could serve as a control group because it would be unaffected by the policy and potentially would be affected by all of the other factors that are going to change hospitalizations in Los Angeles. So the idea here is it's going to be a good control group. It's unaffected by the policy, and if any of the factors affecting hospitalizations that are changing over time in Los Angeles also change by a similar amount in San Diego. So once we have a control group, then we can compute this difference in differences estimate. And the way that we do it is as follows. So as the name implies, it really is just a difference in two differences. So I'm just going to increase or like expand the subscripts here on the variables now because we need to think about both a geographic dimension and a time dimension. So now instead of just having yi, we're going to have yit. And so that's going to be the outcome for, in this case, county I in year t. So I equals 1 is going to indicate Los Angeles, and I equals 0 is going to indicate San Diego, and then t equals 0 is going to indicate 2009, and t equals 1 is going to indicate 2010. So the way that I've coded these things up, basically, one of the subscripts being set equals 1 is going to correspond to either a treated geographic area or a treated time period. So I equals 1 is the treated county because it's Los Angeles. That's where the policy is implemented. And then t equals 1 is going to correspond to the treated period, which in this case we just have like 2 years of data, so it'll be the treated year. So if either one of these subscripts is 0, then you know that the policy cannot be in effect either because you're in the control county or you're in the pre-treatment period, or potentially both. But when both of these subscripts is equal to 1, that's essentially when the policy has been turned on or activated in that particular county. So we can then think about, or we can write down like the change in Los Angeles hospitalizations. So that's going to be y11 minus y10. So y11, remember, that's going to be Los Angeles in 2010, which is after the policy has turned on. Y10 is going to be Los Angeles in 2009. So the difference between those two quantities is just the change over time in Los Angeles hospitalizations. And then the change over time in San Diego hospitalizations is going to be the same, except now you have y01 and y00. So we've set the I subscript equal to 0 now instead of being equal to 1. So y01, that would be hospitalizations in County 0, which is San Diego, in the post-period, which is 2010. And then y00 is hospitalizations in San Diego during the pre-period, which is 2009. So you're just getting the change in San Diego hospitalizations over time. So you've got those two differences, and then you can take a difference of those two differences, which is where you get the difference in differences terminology. So it's going to be the change in Los Angeles hospitalizations minus the change in San Diego hospitalizations, which is given by this expression of the two differences being different from each other. So what's important here is the intuition, which is that any omitted variable that changes hospitalizations in Los Angeles should ideally also change hospitalizations in San Diego by a similar amount. So if that is true, then you're going to get then the resulting estimate that you get from this procedure will represent a causal effect of the policy on hospitalizations. If it's not true, then you're still going to have an omitted variables bias problem. And the intuition, I think is hopefully pretty simple, which is that you're basically just going to net out the omitted variables bias by subtracting off this difference in the change in hospitalizations in San Diego. So like we're looking at the change in hospitalizations in San Diego during the period at which the treatment is turning on, right? So we know the treatment doesn't actually have an impact on hospitalizations in San Diego because it's not coming into effect in San Diego. So anything that we observe here for this difference for the change in hospitalizations in San Diego has to just be due to changes in weather, or economic trends, or crime patterns, or whatever else might be affecting hospitalizations, right? So hopefully, so we observe some non-zero change there potentially, and if we observe that non-zero change, what we're thinking is that we've captured all of the omitted variables, or we're hoping we've captured all of the changes in omitted variables that might also be affected. They're certainly affecting San Diego because there's no policy effect there, and might also be affecting Los Angeles. So if we sort of net out that change from the Los Angeles change, the idea is that we'll basically net out the omitted variables bias. So we can actually sort of look at that algebraically as well. So let's suppose that there is an omitted variable which we'll call ZIT, which affects YIT, and we don't have data on ZIT, so we can't actually just include it as a control in the regression. So let's say that the effect of ZIT on YIT is alpha, and let's say that ZIT is changing by delta units in both Los Angeles and in San Diego. So if that's true, then the effect of ZIT on the change in Los Angeles hospitalizations is going to be equal to delta times alpha, because we know that delta is the amount that the variables change, and then alpha is the effect of that variable on YIT. But likewise, since it's also changing by delta units in San Diego, it's also going to have an impact on San Diego hospitalizations. So the change in San Diego hospitalizations due to the changes in that variable will also be equal to delta times alpha. And so when we do the difference in differences estimator, where we take the change in Los Angeles hospitalizations and then net out the change in San Diego hospitalizations, those two delta alphas are just going to net out from each other, and you're going to end up with a difference that's equal to 0, which is exactly what we want. So saying that ZI here, this omitted variable Z, is not going to cause a bias in our difference in differences estimator, because the effect that it has in San Diego is going to inform us about the effect it would have had in Los Angeles, and we can essentially net it out then. So that's true if ZIT changes equally for both the treated and the control group. So basically, in this case, both in San Diego and in Los Angeles. If that's not true, ZIT is say changing a lot in San Diego but not in Los Angeles, or vice versa, then this differencing technique is not going to work. What might be a little bit less obvious because of how I wrote up the difference in difference estimator, but is nevertheless true, is that it's also going to net out any factors that differ across the treated and control groups that are constant over time. So let's suppose that, again, there's some omitted variable whose causal effect on YIT is alpha, and let's suppose that Z is different in Los Angeles than it is in San Diego, so it's a different level of this variable in Los Angeles than in San Diego, but that variable doesn't change over time. So it's going to be equal to, let's say, Z star in Los Angeles in both years, and Z star star in San Diego in both years. So Z star and Z star star are not equal to each other. So you might think, oh, well, we're talking about like changes in Z being equal in both of these counties, and now we're talking about like a level being different, and so maybe Z is going to introduce some sort of bias. But it still, in fact, will not introduce bias here because of the fact that it's constant over time. So the change in Los Angeles hospitalizations, if we write it down, remember, so Y11 is hospitalizations in Los Angeles, which is a function of all of these different variables potentially, but one of them is, we know, like Z, which has some coefficient on alpha. So the contribution of Z to hospitalizations in Los Angeles in the post period is going to be alpha times Z star, because that's the level of Z in Los Angeles. But in the pre-period, since Z hasn't changed, it's also equal to alpha times Z star. So inside just the change in the Los Angeles hospitalizations, the effect of Z is going to be netted out just because Z is the same in the post period as it is in the pre-period, because we said that it isn't changing over time. Likewise, in San Diego, Z has a different level, say Z star star, but again, since it's not changing pre versus post, it's just going to get netted out in the first difference there. So in the difference in differences, then Z won't end up causing any sort of bias here, despite the fact that we don't have data on it to allow us to include it as a control. So if it differs in the treated control groups, but it's constant over time, then it's not going to bias the difference in differences estimator. So whenever you see one of these designs, what you really need to think about is thinking of factors or omitted variables that change over time in different ways for the treated and control group. So that's the type of factor that could potentially cause a bias in your difference in differences design. So again, let's just think about this. The third type of factor in an algebraic framework. Let's suppose that we have this variable Z that has an effect alpha on Y, and let's suppose that now it's changing by a different amount in Los Angeles than it is in San Diego. So it's changing by delta star in Los Angeles and delta star star in San Diego. So now when we look at the effect of a change in ZIT on the change in Los Angeles hospitalizations, it's alpha times delta star. So the effect of the variable times the change in the variable, which in Los Angeles is delta star. In terms of its effect on the change in San Diego hospitalizations, it's alpha times delta star star. So when we take the difference in differences, its contribution to the difference in differences, we're going to get alpha delta star minus alpha delta star star. Since these two factors are not equal, you're going to get something that's not equal to 0 unless alpha is equal to 0, in which case C is a fully omitted variable anyway because it has no effect on Y. So in the difference in differences studies, what we worry about then are these omitted variables that might change differently over time for the treated group versus the control group. So another way to sort of think about this intuitively, right, is that so what we'd like to be able to observe, we have this policy that turns on in Los Angeles in 2010, right? And so what we'd really like to know is what the counterfactual trajectory of the outcome would have been had the policy not been put into effect, right? Like we see that, say, hospitalizations decreased, but we don't know if they would have decreased anyway, even absent the policy coming into effect. And so fundamentally what we have essentially is what you could think of as being a missing data problem. Like we would like to know what that counterfactual trajectory of the outcome would have been, but obviously since the policy actually got implemented, we can't observe the counterfactual trajectory. So instead we're going to use a control area, in this case San Diego, to try to inform us as to what the counterfactual trajectory of the outcome would have been. And in that case, so that strategy of using San Diego as to inform us as to what would have happened had the policy not been implemented in Los Angeles, like whether that strategy is going to work or not is going to come down to whether or not San Diego turns out to have been a good control group for Los Angeles, in the sense that everything in Los Angeles that was changing that could affect hospitalizations, other than this policy, all of that stuff also happened in San Diego. So if it is the case that all of those factors that are sort of changing Los Angeles behind the scenes also change in San Diego by the same degree, then you're good. You have a good control group that informs you as to what would have happened in Los Angeles absent the policy change. But if it's not true, then you're going to basically make biased inferences because you're going to think like, okay, well, in San Diego I see that hospitalizations were say flat, therefore I assume that hospitalizations would have been flat in Los Angeles absent the policy. I in fact see that hospitalizations decreased, therefore the policy had an effect. But if something else was happening in Los Angeles like changing that affected hospitalizations and that same factor wasn't changing in San Diego, then you still haven't basically accounted for that factor and generated a biased estimate. Okay, so let's just wrap it up there. On Wednesday, the last thing I want to talk about is that essentially it's possible to implement the differences and differences estimated that we just discussed within a regression framework, and there are some benefits to doing that. So we'll talk about that and then move on to getting towards sort of the first empirical studies, hopefully.